So my name is Lynn Kaluzienski. Today I'll be talking about how icebergs affect how iceberg habitat is affected by glaciers and ocean processes. This is work that I've been doing in Glacier Bay, and particularly I've been focusing on glacier seal interactions. So this is work done with Jason Amundsen here at UAS, as well as Andy Bliss, Jamie Womble, and Linnea Pierce at the Glacier Bay National Park. So a bit of background. Coming from my Antarctic background, I often focus solely on sea level rise, so not really looking at ecosystem interactions. I feel like we do a really good job now looking at ice-ocean interactions, and we, as glaciologists, collaborate a lot with oceanographers, but we don't often look at interactions with glaciers and their ecosystems. And overall, glaciers can affect their ecosystems in many complicated ways, like this graphic. Glacier plumes entrain zooplankton, phytoplankton, bring it to the surface where fish can use it. And then, of course, this affects salmon spawning. And what I'm going to be focusing on is interactions with seals within a fjord. Mostly I'll be focusing on how they use icebergs as their main habitat. And so the main question, overarching question, is how do changes in glacier dynamics affect harbor seals and the fjord ecosystem in general? So this talk I'm going to break up into two parts. The first part is looking at long-term glacier dynamics. So we'll be looking at a particular glacier in Glacier Bay National Park, one that's advancing. So this particular this example of a glacier is advancing, slowing down, developing moraine, and all of this has implications on the iceberg habitat within that fjord. So this work is all wrapped up in a paper in Annals that came out earlier this year. So that'll be the focus of the first half of the talk, and then the second half we'll be focusing more on short-term fjord dynamics. So looking at things like circulation patterns, which we can get from iceberg tracking, from time-lapse cameras, and then comparison to plume dynamics and where seals are located. So this is work that is sort of in progress, and so I'm looking forward to getting some feedback for this section of the talk. Okay, so tidewater glaciers are important ecosystems for harbor seals. In one way, ice provides a stable platform for seals when they nurse and rest. So seals often choose fjords as their main place in June and August. So in June is when this is the nursing season, and around August is when their molting season is. These fjords also are thought to prevent predation, for example, from orcas. Things like the high noise levels and turbidity of fjords might make it hard for those to hunt in that area. And one of the reasons that seals choose these icebergs is because it's a stable platform. So they have to choose between whether or not to stay in the fjord or along the sides of the fjord. When they're on the side of the fjord, they're going to have to deal with the changing tides. Whereas in the middle of the fjord, they don't have to worry about that. But there are other trade-offs. So they have to dive for longer periods to forage for food if they're in the middle of the fjord. So there are some trade-offs of why they choose icebergs. And to give us a case study, so there's been a lot of photographs from
somehow, Lynn, you've become muted. just over the last few seconds.
Okay, I think because I was trying to move this bar. Yeah, oops, nope. Yeah, I'll just leave this bar. Okay, so one of the most rapid retreats on record that we have is the retreat of Muir Glacier, and this is within Glacier Bay National Park. So we see on the top, this is a photo from 1941 to 1950, a really rapid retreat, and then to where it is now in 2004. So in the 70s, our seal counts were around 1,500 within that particular fjord. And the glacier itself retreated onto land in the 1990s. And so many of these seals have since migrated to Johns Hopkins Inlet, which is the focus of our work. So Johns Hopkins is within the western arm of Glacier Bay National Park. More than 2,000 seals occupy Johns Hopkins Inlet during the pupping season in June and molting season in August. So this is where most of the vast majority of seals within the park choose their habitat. This glacier is interesting in that, so it's a tidewater glacier and it's currently in its advancement phase. So it's advanced over 1.5 kilometers since the 1920s. On the right is an example of how the glacier has been advancing. This is since the 1940s. And so one of the reasons we've actually chosen this particular fjord to study, other than the fact that this is where most of the seals are residing, is also that it has a long record of surveys carried out by the National Park Surveys. So aerial surveys have been going on for the last 2 decades. So there's a really long record for this particular area. So some of the remote sensing data sets I have worked with, again, this is to pull together sort of the long-term glacier dynamics at Johns Hopkins Inlet. So we focused on the time period from 2000 to 2020. We pulled velocity data sets from ITSLive and then later Landsat 8, Sentinel-1, and Sentinel-2. The aerial photographic surveys were carried out from 2007 onward. And then we've also looked at some sparse DEM elevation data, and then also some multi-beam bathymetry throughout that time period. Right, so on the right is an example of one of the aerial surveys carried out at Johns Hopkins. So each of those photographs is, so each of those boxes is one photograph. And over 91 surveys were conducted between 2007 to 2019. So a few happening in June and a handful happening in August each year. And then this is used, or at least the biologists have used this as object-based image analysis. They've located seals within those photographs, and then we've used it to quantify iceberg concentrations. So the top left is an example of one photograph from that aerial survey. So each survey generates approximately 1,200 photographs, and this footprint is about a size of 120 by 80 meters. You can see some examples of seals that you can easily pick out, as well as pups. So the biologists have gone through and counted all the seals and where they are within the fjord. But we've seen this data set as a great opportunity to go back through and look at ice coverage through time. So we've used an approach that's similar to McNabb and others. So it's using OpenCV and this iceberg segmentation method goes through and it uses a combination of thresholding and edge detection to pick out icebergs. And so then it finds all closed regions or contours within an image, and then it can calculate the area. So we have an idea of the amount of ice coverage from 2007 onward. And this is actually This method has worked fairly well. We've had some issues when icebergs are closely packed. So sometimes the small icebergs will be kind of clumped together. And then we've had to throw out any photos where there was brash ice because the algorithm can't really handle that or decipher between brash ice and icebergs. So moving on to some of our results. So this has got quite a lot on it. We'll walk through it. So the top plot is the velocity from 2007 to 2022. And so you can see when seasonal velocities are available. So this is when Sentinel-1 and Sentinel-2 come online. We can really not just get an average velocity, but really get those seasonal swings. Overall, the velocity record indicates a gradual slowdown, especially from 2013 onward. During that period, the velocity is decreased by about 45%. I don't have the elevation on this particular plot, but I do have terminus position, so that's what's in the second plot. And between 2007 to the end, the terminus of Johns Hopkins Glacier has advanced about 230 meters, and it's thickened by about 23 meters. So what's interesting is that when we were going through some of the photographs from our aerial surveys, we actually saw this moraine pop up at low tide. So this is a photo from 2019. And we went back through the photos, and that was the first time we were able to actually see this surfacing of the moraine. And we see the impact of this moraine on glacier dynamics throughout. One way that it's affected the stability of the glacier is you can see before the formation or the surfacing of the moraine, we had these seasonal swings in advancement and retreat each year, and it seems to have stabilized since that point, now that it's quasi-grounded. So also, along with the reduction in glacier velocities and the shoaling of this surface, the surfacing of this moraine, we've observed a reduction in ice fraction. So the bottom two plots are showing ice fraction, which is the iceberg area divided by the total survey area, and then seal concentration, which is the number of harbor seals divided by the total survey area. So we've also seen a reduction in both of these. So we also looked at available bathymetry data. So we've had data available from 1972. They did one line, which is you can see in the this white line is showing where they were able to survey in 1972. In 2009, they did a very good survey. So this is plot on the left is showing you the bathymetry from that survey in 2009. And then they went back in 2020 and were only able to survey a small portion. So on the right, this is the difference between the two. So this is looking at sedimentation rates over that time. So we were able to find a sedimentation rate of around 1 meter per year. So this is between 2009 to 2020. And so this amounts to about 10 meters of sediment added over that 11-year time period. So this glacier is both advancing, depositing a bunch of sediment out in front of it, and of course it's been developing this moraine through time. All right, so we also looked at our iceberg size distribution. So on the left, we're comparing our seal concentration for all of our data sets versus our ice fraction. And it's broken up to the June months and the August months. But we found that the seal concentration appears to depend logarithmically on ice fraction. So this suggests that the change in ice availability will influence the number of seals in the fjord. This is especially true when ice coverage is very low. So we found through time that the ice coverage has been decreasing. But we haven't found a large variation in iceberg size. So on the right, we're showing the size distribution from 2007 to 2021. So on the bottom, we have the iceberg area. And on the left, we have the probability that that iceberg is going to be larger than a certain size. So at the top left, we have very few really large icebergs, and towards the bottom of each of these plots, we have a large number of really small icebergs. And so in general, we didn't find a change in the shape of this graph. So the relative number of small versus large icebergs per year hasn't changed, despite the fact that ice fraction in general has been decreasing. So this allows us to draw one conclusion. So just sort of putting all of these long-term dynamics together, what we've been seeing at Johns Hopkins is that there's been a terminus advance. This has led to moraine growth, and this has reduced ice fluxes, so less calving. And then the fact that there are less icebergs in general means there's going to be fewer large icebergs, and thus fewer habitable icebergs for seals. And we've actually, in the last few years, we don't have numbers on this yet, we've seen the seals, we've seen less number of seals, but we do in Johns Hopkins, but we do think that they're migrating to a nearby fjord. So the McBride Glacier is another glacier within within Glacier Bay National Park. And it's actively retreating, calving off many icebergs, and that's where we think that the seals are starting to migrate as their next location. So this is an example of a direct link between glacier dynamics and seals. So they're altering their behavior based on this changing glacier. So wrapping up this section of the talk, in general, we've seen from the period of 2007 to 2021, we've seen around 160 meters of advancement. The glacier has thickened around 23 meters, and then has exhibited gradual slowdown. In the later part of our survey from 2013 to 2021, the velocity decreased by around 45%. So along with this slowdown was a decrease in ice coverage and harbor seal concentrations. Again, this is just for the months of June and August, but that's the main time that these seals are utilizing this area. We've also seen the influence of this growing moraine. So we've seen a reduction in seasonal retreat, and overall we've seen iceberg discharge decrease. And this is a fact that the terminus is increasingly grounded. And then even though we've seen that there's less ice in the fjord, we haven't noticed any changes in the iceberg size distribution. So this means that the iceberg size distribution has more to do with calving and fragmentation processes than whether or not the glacier is changing in any other way. And so this provides a direct link between glacier dynamics and seals, in that we expect to see the same thing in other advancing glaciers. So we believe that when we have an advancing glacier, once we have a moraine that's growing, long term, we're going to have a reduction in ice flux, and then fewer habitable icebergs for seals. Okay, so moving on to looking at short-term dynamics within Johns Hopkins. So the main method that we use here is that of time-lapse cameras. So we deployed 4 cameras each year in the years of 2019, 2021, and 2022. So these cameras were deployed around June and taken out around December. Of course, that is dependent on field conditions. So on the right is an example of where the locations of the cameras. So we had two towards the front, pointed towards the glacier and towards the fjord, and then two looking all the way down the fjord from the far end. So these time-lapse cameras take photos every minute during the daylight hours, and we've been able to use this to quantify fjord circulation patterns, and this is from iceberg tracking, which I'll talk about in a second. One of the main issues that we've run into is actually that of bears messing with our time-lapse cameras. So in the bottom left, you can see this is a bear cub messing with one of our cameras. You might be wondering, why is how did we get this photo? So this photo was taken by the other camera that was in tandem with this one. And so what happened was one bear rotated the camera so that it was looking at the other camera and then proceeded to mess with that camera. Here's another example. This is the last photo from one of our time-lapse cameras in 2021. We got a nice close-up of the bear. We're pretty sure that it heard the shutter and freaked out because all of the rest of the photos were just of the sky after this one. So due to this, multiple cameras went down in 2021. And so we decided to focus more on 2019 and 2022, where we actually got decent data. So here's an example of the iceberg tracking method. So this is using a method laid out quite well by Christian Kienholz in a paper he produced in 2019. So this is an example at Johns Hopkins. So this feature tracking relies mostly on OpenCV. But it's tracking the icebergs from photo to photo, and you get these oblique vectors laid on top through time. And this actually works pretty well at Johns Hopkins. So Christian did this at LeConte, which has tons of icebergs. So he got a lot more vectors, but this still works quite well, even though we have a lot less icebergs in this particular fjord. The trickiest part of this method is actually the camera calibration step. So we're matching points or picking out points along the shoreline in these oblique photos, and then we're trying to match them with fjord outline from orthometric satellite imagery, so an overhead view. So to do so, we have to create a camera model that takes into account the camera angle, focal length, things like yaw, pitch, and roll. So that's by far the most difficult part of this framework. But once we build our camera model, we can project our vectors into map coordinates. So this is showing data from 2019. So on the left, we see all of the vectors for through time. And you'll see over here, this is showing the actual photos from the cameras. Our cameras weren't operating at the same daylight hours, so some of them kind of turn on and off compared to others. But you can see this is a really robust data set, provides tons of data. So the way that we sort of break that down is we break our fjord into 150 by 150 meter grid cells, and then we take the average velocity within that grid cell on a 30-minute interval. And once we do that, we're able to create a streamline plot. So this is just another example from 2022. Yeah, actually one of our cameras went out almost immediately. So we were just left with 3 cameras in this particular year. Okay. So once we take those 30-minute averages, we can we can look at different scales or time scales for streamline plots. So this is an example of daily circulation patterns. So these are just, each of these are the daily average flow. So these are just typical patterns that I've seen. Again, this is a really massive data set. So a couple patterns that have really jumped out is that on days of really high velocity, we have uniform flow, versus days when we have really low velocities, we're really seeing a lot more eddies and kind of chaotic flow. And the main thing to remember about this method is that this is just surface flow that we're seeing. So these vectors don't really reflect what's happening at depth. So one of the reasons we think that this particular pattern happens is because on days when there are high katabatic winds or runoff, that's going to dominate surface flow. So you're not going to see any of that upwelling signal or eddies on those particular days. But when katabatic winds are low or runoff is low, that's when you see these interesting eddies form. We also, I wanted to show common locations of eddies. So I typically see an eddy in the bottom left of the fjord, so near the terminus. And there's another prevalent eddy on the far left-hand side of the fjord. And then in 2022, I actually found a new eddy form, or one that I hadn't seen in 2019 anyway. And it formed on this right-hand side. And so we think this has something to do with the plume dynamics of this particular fjord, but I'll go into that in just a minute. So that was looking at the daily average. This is going to break up the streamline plots into sub-daily averages. So on the left, we have the morning average, so taking the average for the six hours that we recorded data in the morning, and on the right is the evening data. I also picked out 3 different transects across the fjord to look at the downfjord flow across these transects at those different areas. So on the left, we have the hourly flow for these particular transects versus their distance across the fjord. So for example, you can sort of pick out maybe this eddy over here. Whenever you have negative velocities, you have flow that's going upstream, and so that's indication of an eddy. One particular pattern that I found over and over again was that velocities are often strongest in the afternoon. So when katabatic winds and runoff are greatest, that's what we're attributing it to. So if you look at the right-hand side, you'll see that, especially for transect 2, you'll see a large change in the velocity. So during the morning, there was actually an eddy that reached up into the center of the fjord. So you can see that here in these negative values. But by the end of the day, we have really fast flow. Right, and finally, looking at seasonal variations in circulation. So again, this is looking at these 3 different transects across the fjord. So transect 1, 2, and 3. And then this is looking at the daily average through time for the months of each year. So on the left, we have our data from July to almost October in 2019, and then our data in 2022. So a couple of patterns that immediately pop out. One, we find the most variability in flow across transect 1. Right, and that makes a lot of sense because this is where the outflow and sort of plume dynamics are going to have the strongest signal. That eddy that I found in 2002 on the right of transect 1, you can see it show up here really nicely in this plot. So we didn't have this particular eddy form in 2019, but suddenly it's fairly common for there to be circulation flow in the summer months in 2022. And Also in 2022, there's a typical eddy on the far side of Transect 3, and that was a lot more prevalent in 2022. So this is one way to look at sort of all of the data sets and pick out patterns. And I hope to go into this a lot further in the future. I'm really interested in seeing what we can figure out in terms of the dynamics happening near the glacier. So can we attribute that to changes at the plume that's coming out of the glacier or things like that? So finally, I wanted to compare these nice velocity plots with the location of seals and then also the location of the plume on any particular day. So there's a lot going on in this particular figure, but gray dots are going to be the seals that are hauled out on ice, whereas the orange dots are seals hanging out in the water. So there's actually a ton of seals in the water on this particular day. This was from August 30th of 2019. So it's a particularly hot day. So that's why we think so many of them are in the water, because that was somewhat atypical. And then in brown, we have the location of the plume. And so this is sort of my first attempt at quantifying where the plume is. Essentially what I did is I just went through planet data, planet satellite data, and just handpicked the edges of the plume. So not the most robust methodology, but it gives an idea of what's going on. And the location of the plume actually matches up really nicely with the region of fastest flow as well. So a couple of things we're seeing with the seals, at least on this particular day, that are on ice are found in the eddies and along the edges of the plume. Whereas the seals that are in the water are really inside the plume near the terminus especially. So maybe they're foraging on that particular day. We can compare this with another day. So this is a day earlier in August, so August 12th. And in this particular day, I had issues really picking out the location of the plume. The plume was a lot more dispersed on this particular day, and so delineating what I want to call plume versus not plume was somewhat hard. So this is sort of the limitations to this method. But on this particular day, we also found a ton of seals at a recent calving event. So I don't have this labeled, but the red area near here was an area where there were tons of icebergs that recently calved. I was able to pick that out from planet imagery as well. So we found the seals, tons of seals hanging out in that area, which makes sense since there's tons of icebergs there. And then again, I'm seeing a lot of seals hanging out on ice that I believe is at the edge of the plume. Again, it was just hard to delineate where the plume was on this particular day. So I also just compared seal locations versus flow speed. So this is only for 2019. I still have to go back and do the same analysis for 2022. So on the top, we have the number of seals that are on ice for a particular flow speed. And then on the bottom, the orange is the number of seals that are in the water and what flow speeds we typically found those at. So from these plots, the majority of seals seem to haul out on icebergs within low velocity regions, whereas seals found within the water column appear to utilize faster currents. One issue that I'm running into, though, is the reason that we're seeing more seals on slow-moving icebergs is that due to the fact that the seals actually prefer slow-moving icebergs, or are there just more icebergs in low-flowing, low-velocity regions? And that I'm kind of struggling with how to actually piece that out with the data. Okay, so wrapping up our short-term impacts, we found iceberg velocities to be weaker and more variable in the morning. And they typically became more uniform and stronger in the afternoon, which we attribute to a higher chance of katabatic winds and runoff. We found the flow to also have the most variability near the glacier terminus. And the seals that we were able to observe within the fjord appear to prefer icebergs on the edges of flumes or in regions of recent calving events. And we also believe, well, the majority of seals haul out on icebergs within low velocity regions, whereas seals that are within the water column appear to utilize faster currents. So with that, I will conclude my talk and hopefully open it up to discussion.
Thank you very much indeed. So the way that we usually do questions is we ask people to either put their hand up or to pop onto the chat that they want to ask a question, and then we get people to unmute to ask a question. So I don't know if anyone would like to start the discussion. Roger, go ahead.
Yeah, thanks very much, Toby, and thank you for the talk, Lynn. Much enjoyed that. Question about your sort of seal concentration per square kilometre. It's a nice unit. I'll apply it to some seismic at some stage. What sort of uncertainty bounds are there on those measurements about how many seals there are per square kilometre, given the methods you've used?
Yeah, so that's a good question. And actually, so the biologist, I know Jamie Womble actually thinks about the ways to quantify seals and number of seals in many ways, or in depth. So I'd say, I don't know if I have an exact number. I'm trying to pull up a figure. Let's share screen. I think the way to answer that would be to look at actually how much coverage we get versus areas that we aren't covering. So this is just an idea of where we're getting photos versus not. We also tended to throw out some of the data on the sides. Sorry, I'm running into issues. Yeah, it's not letting me see you guys when I have this in this mode, which is really annoying.
We can still see you and the slide. We've got a bit of Zoom mess on top, but we can see.
Oh, show video panel. There we go. That's a little bit better. Sorry. It's hard to just talk out into the ether. Yeah, so I'm not sure if that answers your question, Roger.
Yeah, I presume therefore within any given photo, you're completely confident you've got every seal there is, but then there are a few gaps, which is understandable. I just wonder if there are any small seals or any that are hiding somewhere that might modulate.
Yeah.
I mean,
well,
are there any factors outside the fjord that will change the number of seals bothering to go in there? I just don't know about marine biology, whether or not some outside or a good shoal of fish or whatever the hell will keep them all away and bias your numbers.
Yeah, so going back to your first question, we're pretty confident that we find all of the seals that are on icebergs. They're very easy to pick out. And the Linnea Pearson's the person who went through that data set, and she's pretty confident. But seals in the water, right, that's only going to be seals near the surface, and they dive quite far. So there's tons of seals in the water that we're not getting. Yeah, so hopefully that helps answer that question. Talking about what would cause seals to perhaps not return, I don't know if I have a good answer to that, but I can say that Jamie Womble spent a lot of work studying these harbor seals in this particular fjord, and she did a tracking study, and it turns out that the harbor seals in general have a really high fidelity for a particular fjord. So something like 90% of the seals would return year after year to their particular fjord. So the fact that they are not returning towards recently, yeah, I would attribute more to what's going on within the fjord. And hopefully we'll get more data on where they're going. Like if we could actually track and see if they are migrating to McBride, for example, I think that would be a really interesting study.
I think cool. Thanks very much. I mean, good to see there's fun life after Antarctic geophysics. I'll tell our PhD students doing Antarctic geophysics.
Yeah.
Yes.
Just a quick one from me before I pass over to Andrew. I was intrigued that you said the seals were sort of returning. Are they doing a kind of annual migration that comes into the fjord and then goes out? Is that? I don't know enough about seals to know what their yearly is.
Yeah, no, that's a good question. Yeah, they travel quite far, and they do come back to the fjord, and they actually I believe that they'll come in and out of the fjord daily as well. So I'm not sure exactly where they're going when they're at night, but I do know that they sort of migrate in and out of the fjord over time. Yeah.
Thank you. Andrew, you've got your hand up.
Sure. Nice job on the talk, Lynn. I was just wondering how much of the eddy structure that you see in the fjord might be due to the specific camera angles that you had in one year compared to the other year. Does that make sense?
Yeah, I think I can go back. Sorry, thinking about this, right? So yeah, I think that's a good question, but we did try to keep the cameras as close as possible, but I do know that we chose a different area, and our near fjord camera in 2019 was a little bit different than in 2022. Let me go back to that seasonal one. But the cameras that are at the far end of the fjord are really close, and we try to give them a particular angle and be really specific about it, because our camera model also depends on those angles. The better we know what they are, the better off we are later on trying to match our photos. So yeah, that might be worth something sort of investigating on maybe Transect 1, but I don't think it would affect what's happening down at Transect 3. I think these are definitely comparable, but that's definitely a good thing for me to look into. So thanks.
Are there any other questions for Lynn?
Yeah, I have one. I wrote in the chat. This is Paco.
Oh, sorry. Yes, I now see it. It's suddenly appeared. Paco, go ahead.
Okay, nice talk. I enjoy it. I have just I'm curious about when you mentioned about the count of seals, and whether even you suggested the possibility that they were living maybe some daily. and sometimes. Have you made some kind of tracking or comparison between the total number of seals that you can count on subsequent days with similar conditions?
Oh, that's a good thought. I'd have to go back into some of the previous research because I don't think they've done any tracking of seals in quite a well. It's been a few years since they've done any tracking studies. Yeah, I wonder, Andy, do you know if Jamie's ever tracked seals on like? So I know she's tracked them at the end of the season and then watched them come back the following season. But yeah, wondering if you have any insight on that.
No, what I was meaning is that if you have subsequent days with similar conditions, number of icebergs and so on, then I would expect that the numbers of total number of seals should be about the same, and that could provide even some kind of estimate even in your error in counting. But if you say that they can be living daily, then there's a problem also.
Yeah, that's a good point. Sorry, Andy, did you have something to say? Sorry.
Yeah, I think that we do have surveys, like duplicate surveys, one day and then the following day, for example. So either Jamie or Linnea would have a better sense of what that actually tells you about uncertainty and what proportion of seals you're seeing in a given survey. But I'm not as familiar with all those papers as I should be. So leave it at that for now, I think.
Okay.
Okay,
yeah,
thank you.
Yeah, that's what I was about to say too, is that I guess I don't have them plotted here, but I think we definitely have yeah, so sometimes they'll do a survey. For example, I think they did one on the 31st as well. So we have back-to-back days. I will say that the circulation can be quite different, even though it's around the same period. It's just that variable. But that is a good idea for me to go in and see what I can, yeah, what I can sort of figure out.
Okay, thank you.
Thanks.
Any last questions for Lynn? If not, I think it's just falls to me to say thank you very much for such an interesting and interdisciplinary talk. Thanks, Gwen. Perfect wording there, just appeared on the chat. Oh, yeah, I think that one's a joke question from Roger.
Yeah.
Thanks very much indeed, Lynn. And there's no more IGES seminars now until after Christmas. Next week is AGU, so we've decided to finish seminars for until the new year. So thanks very much to everyone for attending, and see you after New Year.
Awesome. Thank you so much.
Bye.
Bye.